Your weekend is ruined. Not by you. Not by your boss. By a butterfly. Specifically, one that flapped its wings 3 weeks ago over the Indian Ocean. You have no idea who this butterfly is. You've never met. And yet here you are, standing in the rain, holding a soggy hot dog at what was supposed to be an outdoor concert. That's meteorology. That's the whole thing. Welcome. Okay, but before we get to the butterfly, and we are absolutely getting to the butterfly, we need to start somewhere even more basic. We need to start with something you've felt every single day of your life, without ever really thinking about it. Heat. Specifically, the completely unhinged way heat moves through the atmosphere. So here's the question. Why does heat rise? And? Like, why doesn't it just stay put? You turn on your stove, the burner gets hot, and somehow your whole kitchen ends up warm. But the heat didn't teleport. It traveled. How? And? Here's the thing. Heat doesn't just move, it drags stuff with it. When air gets warm, it expands. Molecules start bouncing around faster, spread out, take up more space. And because the air is less dense now, the atmosphere around it basically goes, "You're lighter than me, get up there." So the warm air rises. And the cold air, denser, heavier, more serious about life, sinks down to take its place. This loop, warm air up, cold air down, warm air up, cold air down, that's convection. That is the engine of all weather on Earth. Every storm, every breeze, every time your umbrella betrays you. It all starts here. Now imagine this happening, not in your kitchen, but over an entire ocean. The sun heats the surface of the water. The water heats the air above it. That air starts rising, and as it rises, it cools. And here's the thing about cool air, it can't hold as much moisture. So that moisture has to go somewhere. It condenses. It becomes clouds. It becomes rain. The rising air creates a low pressure zone at the surface, because all the air left. And the surrounding air, being the overachieving dense stuff that it is, rushes in to fill that gap. You now have wind. You have clouds. You have the beginning of something. This is literally how every storm on the planet starts. Warm surface, rising air, condensation, low pressure, wind. That's the recipe. But okay, here's where it stops being simple. Here's where the Earth itself decides to get involved and make everything exponentially more complicated. You ready? The Earth is spinning. You know this. You've always known this. But here's what you maybe haven't thought about. That spin does something to the air. Something deeply weird. Something that turns a simple column of rising air into a spiral. And that spiral is the reason hurricanes exist. That's next. Okay, so the Earth is spinning. Cool. We knew that. But here's what nobody tells you in school. The spin doesn't just move the Earth under your feet. It deflects everything moving on top of it. Air, water, missiles, anything traveling long distances across the surface gets bent. This is called the Coriolis effect, and it is one of the most counterintuitive things in all of physics. Not because it's complicated. Because it feels like cheating. Here's the best way to picture it. Imagine you're on a merry-go-round, the big spinning kind, at a playground, and you throw a ball straight across to your friend on the other side. From your perspective, the ball curves. It doesn't go straight. It bends. But from above, from someone standing off the merry-go-round watching, the ball went perfectly straight. The curve wasn't real. It was the rotation underneath it that made it look curved. That's exactly what the Coriolis effect is. Air tries to travel in a straight line. The Earth rotates underneath it. From our perspective, standing on the rotating surface, the air looks like it's curving. In the northern hemisphere, it curves right. In the southern hemisphere, it curves left. Always. So now take that low pressure zone we built in part 1, that gap where warm air rose and left a vacuum at the surface. Air rushes in from all directions to fill it, right? But the Coriolis effect bends every one of those inrushing streams. They don't fill the center cleanly. They spiral, counterclockwise in the north, clockwise in the south. Add enough heat, enough moisture, enough ocean, and that spiral tightens. It feeds on itself. The warm ocean keeps pumping energy up. The system keeps rotating, keeps intensifying. That is a hurricane. A heat engine. Wah. A spinning column of atmospheric chaos that can be 500 miles wide and carry more energy in a single day than every nuclear weapon ever built combined. Stop. Let that land for a second. One hurricane. One day. More energy than every nuclear weapon humanity has ever created. And we have them every year. We name them. We track them on apps. We complain about the traffic when we evacuate. The sheer scale of energy the atmosphere moves around on a routine Tuesday is so far beyond anything human civilization has ever engineered that it basically shouldn't be possible to comprehend. But there it is. That is the awe moment. That's the part where you just have to sit with it for a second, because no joke makes it hit harder than the silence after that number. Okay? Back to chaos. So we understand convection. We understand pressure differences. We understand the Coriolis effect. We understand how storms form and intensify. So why can't we predict the weather more than about a week out with any real accuracy? We have satellites. We have supercomputers running billions of calculations per second. We have radar networks covering the entire country. And yet your weather app still lies to you about Thursday. Why? And here's the question that broke mathematics in 1961. A meteorologist named Edward Lorenz was running a simplified weather simulation on his computer. He wanted to rerun a calculation, so he entered the starting values manually, but he rounded one number slightly. Instead of 0.506127, he typed 0.506. 3 decimal places instead of 6. A difference so tiny it shouldn't matter at all. He came back to check the output. Wah! The simulation had gone completely off the rails. 2 weather patterns that started almost identically had diverged into totally different outcomes. Not a little different. Unrecognizably different. That's chaos theory. Not chaos like random. Chaos like extreme sensitivity to initial conditions. The atmosphere is a chaotic system, meaning tiny differences in starting conditions, differences smaller than any instrument can measure, compound over time into wildly different outcomes. Every hour you forecast further into the future, your error doesn't add up. It multiplies. Day 1, you're pretty good. Day 3, decent. Day 7, you're basically guessing with math. Day 14? You might as well ask the butterfly. And that's where the butterfly comes back. The butterfly effect isn't a metaphor. It's a real mathematical property of chaotic systems. One small flap, one tiny air pressure variation over the Indian Ocean propagates through the system, gets amplified at every step, and 3 weeks later, it's the difference between a clear Saturday and the soggy hot dog situation we opened with. The atmosphere is so sensitive, so interconnected, so dependent on every single variable everywhere on the planet simultaneously, that perfect forecasting is not a technology problem. It is mathematically impossible. Full stop. There is a hard theoretical ceiling on how far out weather can ever be predicted, no matter how powerful our computers get. Which brings us to the most important, most underappreciated fact about meteorology. Meteorologists are the only professionals in the world who can be wrong in front of millions of people repeatedly on television and still have a job the next morning. And honestly, that's not a failure. That's science working correctly. They're not wrong because they're bad at their jobs. They're bumping up against the fundamental limits of what the universe will allow us to know. So here's where everything we've built starts to connect into one picture. We have convection, heat moving air up and down. We have pressure differences, air rushing from high to low like water, draining out of a bathtub. We have the Coriolis effect, the Earth's spin bending everything into spirals. And sitting above all of it, about 5 to 7 miles up, there's one more player. One that most people have never heard of, but that quietly controls everything happening below it. The jet stream. It's a river of wind. Invisible, moving from west to east at speeds that can hit over 200 miles per hour. It circles the entire planet, and it forms for the exact same reason everything else in meteorology forms: temperature differences. Cold polar air on one side, warm tropical air on the other. The boundary between those two masses creates a pressure gradient, and the Coriolis effect bends that gradient into a fast-moving river screaming across the top of the troposphere. That river is the jet stream. Here's the thing about the jet stream that most weather apps will never tell you. It doesn't flow in a straight line. It meanders. It buckles. It dips south in massive loops, and then swings back north, and wherever it goes, it drags weather with it. When it dips south over you, you get cold. When it swings north, you get warm. When it locks into a pattern and stops moving, that's when things go truly sideways. A blocked jet stream is why Texas froze in 2021. A buckled jet stream is what steered Hurricane Sandy directly into New Jersey in 2012. It's not just a feature of weather, it is the steering wheel. And here's your cross-discipline plot twist, because we promised those. The jet stream? It's basically the same physics as the Gulf Stream in the ocean. Both are rivers driven by temperature gradients. Both are deflected by the Coriolis effect. Both carry heat from the tropics toward the poles. One does it in water. One does it in air. Two completely different systems, same planet, same equations underneath. Wah. The atmosphere and the ocean are running the same software. The whole Earth is just one enormous heat redistribution machine, and we're living on the outside of it. Now zoom all the way back out. Remember the butterfly. Remember Lorenz typing 0.506 instead of 0.506127 and watching his entire simulation collapse into something unrecognizable. That's not a flaw in meteorology. That's just what the atmosphere is. It's a chaotic system of staggering complexity, where heat, pressure, moisture, rotation, and ocean temperature all interact simultaneously, everywhere, all the time. Current research suggests the hard ceiling on meaningful weather prediction sits around 10 to 14 days out, no matter how good our models get. 2 weeks. That's the universe's budget for telling us what's coming. After that, you're on your own. And we've gotten remarkably good at it within that window. 72-hour forecasts today are more accurate than 24-hour forecasts were 30 years ago. The satellites, the radar, the supercomputers, they've pushed us right up to the theoretical edge. We are not failing at weather prediction. We have nearly perfected it up to the boundary of what is physically possible to know. Which brings us back to where we started. Your ruined weekend. Your soggy hot dog. A butterfly you never met. You now know every step in the chain. Warm surface heats air. Air rises. Moisture condenses. Pressure drops. Wind rushes in. The Earth's rotation bends it. A jet stream steers it. A chaotic system amplifies every tiny uncertainty into something enormous. And 7 days later, it's raining on your parade. Not because science failed. Because the universe is deeply, fundamentally, beautifully unpredictable at the scales that matter to your Saturday afternoon. And here's the open question that humanity still doesn't have an answer to. We know the atmosphere is chaotic. We know there's a 2-week wall. But nobody fully understands why the jet stream is getting wovier. Arctic ice is melting. The temperature difference between the poles and the tropics is shrinking. And some researchers think that's causing the jet stream to slow down and buckle more dramatically, locking weather systems in place longer, making heat waves hotter, making cold snaps colder, making everything more extreme. But we don't know for sure. The models disagree. The data is noisy. We're staring at the most complex system on Earth and asking it to explain itself, and it just keeps raining.